Welcome to Spring LIB.
Okay, in this problem we are asked to find the kinetic energy of ejected photoelectrons given a known threshold wavelength for our particular metal that the electrons are being ejected from. We also know the energy of the incoming light used to eject these photoelectrons. So the main equation we're going to use to find the kinetic energy in this problem is this expression of conservation of energy. Namely, and it'd be useful to have a diagram here to see what's happening. Say we have light incoming with a certain energy. The energy of light is proportional to its frequency, hf. And this, if we know that if this surface, this metal, has a work function phi, then we know that that if energy is incoming at an energy larger than phi, it'll eject photoelectrons with a certain energy k. The kinetic energy that these photoelectrons will have is simply going to be the energy of the incoming light minus this threshold energy called the work function, phi. So we know it. So this expression depends on the frequency of the incoming light and the work function, both of which we don't directly know. We actually can find the frequency of this light rather easily by using this formula, this expression, c equals lambda f. In other words, c, the unchanging speed of light, is equal to the product of light's wavelength and frequency, which if one increases, the other must decrease. So this is an indirect way for us to arrive at the frequency of light given a wavelength. In order to find the work function, we need to manipulate this equation more thoroughly. So the two constants we'll need for this problem are the speed of light, of course. 3 times 10 to the 8 meters per second is a very good approximation. And we're going to use the Planck constant, 4.136 e to the negative 15 electron volts seconds. Okay, so let's jump into this problem. Okay, so first things first, we can get the frequency of our light, which we'll need for later. So using the expression c equals lambda f, we know c, it's a constant, and we know lambda, threshold. This is our threshold lambda for our particular material. So this will allow us to get a threshold frequency. F is going to simply be, well, I should say f threshold is simply the speed of light divided by lambda threshold, which numerically would be e to the 8, e times 10 to the 8 rather, meters per second, divided by our wavelength, which is given to us to be 272 e to the negative 9 meters. Thus, our frequency will be 1.10 e to the 15 hertz. Great. So now, the critical detail worth noting is understanding what these threshold values mean. So when the incoming light is at a particular threshold frequency or equivalently a threshold wavelength, this is the case where the very, very minimum amount of energy to eject a photoelectron is reached. So if we were to eject a photoelectron at this particular wavelength or frequency of light with its corresponding energy, the corresponding kinetic energy of the ejected photoelectrons would be 0. So there'd be no energy left over to give to the electrons once they'd been ejected. So using our equation for the photoelectric effect, K becomes 0, and we're left with this expression. And by definition, we call this the frequency at which this occurs, threshold frequency. So in other words, I should more explicitly, when F is equal to the threshold frequency, it must be the case that the kinetic energy of photoelectrons being ejected is 0. So this fact allows us to arrive at this expression, which will allow us to solve for what the work function actually is for this particular material. And it's going to just simply be equal to the energy of the incoming light, which is the product of Planck's constant and the threshold frequency. So numerically, That would give us Planck's constant, 1.416 e to the negative 15 electron volt seconds. Multiply by the threshold frequency, which we just found, 1.10 e to the 15 hertz, which comes out to about 4.55 electron volts. Great. So now that we know what the work function is, we can now return to the original, the general expression for photoelectrons being emitted. K equals HF minus phi, where this time we're not just looking at the limiting case where F is at the threshold frequency, we're looking at the frequency of the light we actually care about, which is stated at the beginning of the problem. So we know what F is. It is one second. It is it is the 1.45 e to the 5 hertz that was given at the beginning of the problem. So we can now numerically determine K. And it would probably be best to do this in electron volts, using Planck's constant as before, using the given frequency as before, 1.45 e to the 15 hertz. And subtracting the work function, that amount of energy, that minimum required energy to even eject an electron. Crunching these numbers, we're left with 6 electron volts exactly, minus the 4.55, which, as you can see, will give us a resulting 1.45 electron volts. So this 1.45 electron volts is the kinetic energy of these photoelectrons for light coming in at this specific frequency. And this value of the work function is specific to the material that the electrons are attached to, are being detached from. So that's the main result. This is the kinetic energy of these photoelectrons for this particular case.